Okay, cool. Welcome. So thanks for coming all. So as was said, so it's a sponsored talk, but I will try to not make it any advertisement or something like that. So it's really more about, we have open sourced a machine learning library where we're just looking for contributors, building a small community, and this is about, right? I don't want to sell you anything or something like that. Okay, so let's get started, I think. Is it okay? Or? Okay, good. So then, so maybe first of all, so this, if you are looking for something like a new deep learning method or something like that, so you might be a bit disappointed. So this is more like the traditional classic shallow learning stuff. But there I hope that it's quite advanced and that it actually works and you can use it for real world use cases. So this is the idea. So it should be relatively off the shelf in the sense that you just install the library and you're ready to go for many use cases. So this is the idea. And as I said, we are looking for contributors, hoping to grow a community around it. So similar to the case like the big XG boost, right? So it's no boosting, first of all. You will see later on what it is. I will try to explain the method. And yeah, if you have any questions in between, so just ask interactively. That's okay, okay? Good. So first of all, what is it about? So I will explain the name a little bit later on, but it's actually a family of machine learning methods. So as I said, it's the traditional machine learning like you know it from things like random forests or whatever, right? So this kind of thing. It's off the shelf in a sense that, as I said, it's hopefully ready to use. It's general purpose in the sense that you can use it for many use cases. You will see when I talk a little bit why we developed this method and so on, so that we actually developed it on a specific use case, but later on realized that we could use it basically all over the place for structured data. So that means, of course, for things like unstructured data, like computer vision, natural language processing, nowadays you would, of course, use deep learning. So it makes no sense to talk about such methods. So this is really mainly with the focus on structured data, where you would not necessarily need a deep learning approach. And sometimes it's pretty hard to build one, right? Both in terms of the data needs and in terms of tuning the model and so on. And yeah, it's supervised learning for regression and classification, as I said. It's for several cases. We will look at a few in the following. So it's actually a method that is a mix of different ideas. So you couldn't just describe it as something like this is a decision tree or this is something like a linear regression or so. The closest relative actually is generalized additive models. For the ones of you who don't know what it is, so I will explain it a little bit on the next slide, what is behind. But in principle, you can think of it as linear regression, where you have a link function that allows you to, for example, do multiplicative regression as well. And you would not necessarily do it only linearly, but you allow specific terms in between, right? So not like a times x1 plus b times x2. You basically allow the x's to be something more advanced, right? So like a quadratic thing or even interaction term. Okay, so and the main difference to the other methods like generalized additive models or maybe even neural networks is that instead of estimating parameters like the coefficients that I just mentioned or maybe the weights in a neural network, which is basically the same thing, right? It's also just many linear models just stacked together. So instead of having such a parameterized method in the first place, here you actually estimate factors for binned features. So that means for each of your input variables, like the different x's, you basically bin them. You will see in a second how this works. So let's say 10 bins, right? So then you have 10 different categories for each of the features. And for each of those bins, you learn a factor, what is actually contributed to the final result in the prediction or inference. And those factors are estimated. So in a sense, it feels a little bit like a non-parameterized method. But hopefully you will understand when I show you the formula. It's actually pretty straightforward. Okay, but in that sense, it offers you also a kind of individual explainability. So this was one of the main motivations as well in the beginning. And yeah, today I will only show you a pretty simplified version of the algorithm so that you can understand the basic workings. If you want to know all the nitty-gritty details, so we have actually 2 papers that are on archive, then you can read through it if you want. Okay, but as I said, so the main thing today, of course, I want to explain you how it works, but the main thing is actually that we decided after quite some time when we used this, so it's not a new method, we developed it actually several years ago already, we decided that we would want to open source this as well. So we used it internally for many years for different use cases, but now we thought it might be a good time to also not only publish the methods, how they work, but also publish the code, right? That means we have something like a scikit-learn-like usage of this library. It is on GitHub. It's also easily to install, just pip install Cyclic Boosting. And there's also a documentation that admittedly is not super extended yet, but hopefully one can more or less understand how you would use it and how it works. And we are working on it to make it better, of course. Okay, so now I come to the different modes. So as I said, you can use it for several cases. So this might look like now a little bit difficult to understand, but hopefully it's not that much. So when we look at those two, so basically look at this one here, right? So we talk here about regression. So that means your target is a real valued number. So for example, the famous price of a house or something like. I will later on talk a little bit about demand forecasting. So basically when you want to predict the sales on a given day for some article in a supermarket or something like that, right? So this is regression. And sometimes you have it like your target range is minus and positive. It can be anything. So then in such a case, your model usually would be something like a Gaussian, right? So this is what you typically do. So, but if your target is only positive, so then usually your model is also something else. So then often a Poisson distribution or a negative binomial distribution, which is something like a gamma Poisson if you want, or Poisson distribution where the mean parameter is itself gamma distributed. So something like this is better suited. And so in a sense, if you think on generalized additive or generalized linear models, this basically is the typical linear regression case. And this one here would be Poisson regression. So you basically have a target where you have a link function that is the logarithm that basically brings you then from the additive to the order. The inverse link brings you from the additive to the multiplicative space, and then you have also multiplicative effects, and you have this target range, right? So this is the view from a generalized linear model perspective. And yeah, so there are several different other modes. You could easily do this with classification as well. So there, logistic regression, for example, you have the log it as link function, it's the same game, right? So there, your model would be something like a Bernoulli distribution. So I will come later on to the models again, and to the other modes I will describe briefly in the end. So they are not too important to understand the thing. It's always the same thing, right? You have a link function, you have a target range, and this decides about the model topology if you want. Okay. So the use case that I want to describe a little bit, because this was actually where we developed it historically, is demand forecasting. So there, the typical issue with which we faced was that we have a supermarket with many products, right? So like many thousand products, many stores, and we basically have hourly or daily aggregated sales that we want to predict. So that means you have many individual time series that you want to forecast. And something like that might look like this one here, right? So you have a time series, and you have the aggregated sales over a day, for example, for a given product location combination. In this case here, it's aggregated on product groups just for visualization or something like that, okay? And sometimes you see there are large peaks, so they might be due to price reductions or so, if something is in promotion. And usually you see something like a weekly structure, so the typical thing with time series, right? So on such a thing, usually what you do is you go with traditional univariate time series forecasting first, like things like ARIMA or maybe even Facebook's Profit or something like that, right? So the advantage of using machine learning over that, first of all, is that if you learn on all time series together, you can actually make use of the commonalities between them. And by doing so, you can reduce the variance. So that means maybe all products in a given group behave the same thing, right? So they have the same weekly structure or something like that. If you learn it on that level, it's much better than if you learn it individually for each of the time series, right? So this is something like the hierarchical sense of it. And the other thing is that, of course, there you can easily include such things like promotions as external variables, so just features in the model. So this is not that straightforward if you have a typical time series forecasting thing. So this is what we had, and then there were a few subtleties to it. So we started actually with something like a neural network approach back then, which is of course also machine learning and does all these things. But we faced a few issues, like for example, here you have categorical features of very high cardinality. So as I mentioned, products and locations, right? So these are basically IDs, if you want, in the first place. Of course, you can do something like embeddings and so on if you go more advanced. But in principle, these are IDs, and you have many of them, right? And to learn them one hot and so on is super hard. That means you need a method that can take care of that. You have actually mainly multiplicative effects. So like the effect of, or the correlation between a feature and the target is not additive in a sense, but it's multiplicative, so that if you double it, the target is also doubled, something like that, right? And the demand is following typically a Poisson distribution, as I mentioned. And with all these things taken into account, we tried to develop a method that fulfills that and used a few of our old findings from the previous methods, but actually came up with something new in a relatively ad hoc sense first, and later on we formalized it a little bit to fit into that structure of a generalized additive model. So first of all, here look at the prediction view. So this is what I already mentioned, now in a simple formula. So how it actually looks for the multiplicative regression mode, as I mentioned. So here, as I said, there is a variation is proportional to the level. This would be a multiplicative model. This is what I just told you. And how the model looks like, I already said, so we have the spins of the features, right? So we have here the different features. So let's say 10 features that we have. So this is running from 1 to 10, so to say, and each of the features makes a contribution to the final prediction. So let's say 0.8, 1.2 times 2.5, something like that, right? And I already said each of the features comes with a number of bins. So let's say 10 bins or 100 bins or all the different categories that you have. So like your 1,000 different products or so, and each of them gets a bin, right? And for all of these bins, there is a factor learned. And if you do a prediction, your one sample for each of the features falls only into one bin, right? You look it up and you do now the prediction for product number 5, and this is of course only the prediction for this one bin. All the other bins for the other products don't care, right? So that means you do a lookup if you want. For each of the features, look into which bin your sample falls, and then you can easily multiply them up, right, if you have beforehand learned the factors. So, and this is what I said, in a sense, this is kind of non-parametric, because here you have learned factors and not parameters that are multiplied now with the feature value itself. You just, for the feature value, look up into which bin you fall. Okay? So this is kind of the strategy, and of course, you have something like a global target average, which gives you the overall range. And if you do so, then the neutral factor would be 1. And each time you see a deviation from 1, you see how much this feature contributed. And this is kind of the idea of the individual explainability. So let's say you have 3 features, as I said. One is 1, one is 0.8, one is 3.5, right? So then this 3.5 is what drives the prediction up for this one sample compared to the average. So in that sense, you have this intrinsic individual explainability already in. So you should not confuse this with a causal effect, of course, because this is just what the model means, right? So this is no causal assumption about the structure of the data generation process or so. It's really just what the model has learned about the training data, right, in that sense. And yeah, as I already said, it's a machine learning method, so we do the typical machine learning IID assumption, so basically the independence between the different samples, and we treat here each time step as sample. So that means our thing is not only product location, which is one row, but basically also the date itself, if you want, right? So think of a spreadsheet for each product, location, date combination. This would be like the key. This is one sample. And we don't have a sequence model here like a transformer or an RNN, where we basically treat all the different time steps of one time series together in one sample, right? We have one sample for each of the time steps. So that means we don't make use of autocorrelation itself. In a sense, you would have to bring this in again via something like an exponential weighted moving average feature if you really want something like autocorrelation to be treated in. Right? In a transformer, it's a similar thing. So there you do it via the positional encoding. You bring this information in. because you have the permutation invariance. So, okay, forget it. Okay, so now to the training example. So this is kind of the one formula that I said. So how this thing works. So it's actually a coordinate descent method. So that means it's not the typical gradient descent where you look at all the different parameters together in the high-dimensional space and you go to the inverse hill climbing thing, right? So here you basically treat each of the dimensions separately, one after the other. So in a sense, that means you start with all factors to 1 and a global average, and then you cyclically iterate through the features. So that means you look first at the first feature, then look at the second feature, and so on. And for each of the features in each of the bins, so a feature and the different bins, so let's say feature number 1, and now we look at the 5th bin, for example, we first of all sum up all the target values that fall into that bin, and then we sum up all the predictions, and I come to that in a second. In the beginning, this is just 1, right? So it's as simple as that. You sum them up, and you get the factor. And the point is now, you always, when you calculate these predictions, you just spare out the feature that you are looking at the moment, right? So, and then in this non-aggregated view that I show you here, you basically always, in each of the iterations, for each of the features, you calculated anew, right? It's a pretty simple algorithm. You just go through the features, set all of them to the factors that you have already learned in the last iteration, and just calculate now the new one new, right? And you get the feature, you get the factor for this bin out. And this you do for all the features in several iterations according to some stopping criteria in the end, as always. And you get something like a loss out here if you want, so over the different iterations. And this is the procedure, right? It's in principle, on a high level, you can think of it as 3 loops kind of thing. So the typical iterative thing where you go over the iterations, then you have go sequentially, coordinate descent light over the features, and in the end, you have for each of the bins, you do this in parallel, right? The bins are not correlated to each other. This is how the method works. So pretty simple, right? So there are lots of subtleties, as I said. So for example, you could do this with a learn rate. You could do this in a sense that you basically take the values from the last iteration in and do a boosting-like update, whatever, right? But in principle, the idea is exactly like that. Okay, now a few details, because binning is that important. I just want to show you how this works in principle. So for binning, for the categorical features, I already mentioned it's pretty straightforward. We just look, for example, for the product IDs for each of the products independently, and we just learn the factors here. So that means the red dots that you see here are just the factors that are learned. And I show here in the end the truth in each of the bins and the prediction in each of the bins. So that means the smoothed factors is what the model has learned, right? These are the factors in the model, and the predictions and the truth is actually when you just look at this bin and just do the sums that I showed you and divide it via the global average. So I will come in a second why they don't are the same for all of the cases. So yeah, and for continuous features, actually you do the binning before, right? So you either have the same bin width, like with a typical equidistant binning, or what makes more sense in most of the cases, you have equistatistics binning, so that you just look that for each of the bins you have approximately the same number of observations in, and you just vary the bin width so that you can get there, right? And then this is what comes out there. So and this kind of optimization scheme enables, if you want, in a sense, a local optimization in each bin. Because as I said, you look at all of the bins in a feature, and in each of the bins you do an optimization. So this is different to what, for example, linear regression would be doing. So there you are fitting one parameter to get the full feature, right? And we do actually a fit, if you want, in each of the bins. So which is, of course, giving a much lower bias in the end. And you can also do things like interaction terms, as I mentioned. So you could easily do a binning in 2 dimensions, right? So this would be that. So for example, locations and products. We just do the binning in 2 dimensions, and for each of the product location combinations, you learn a factor. Same thing, right? If you want, this would be an interaction term in a generalized additive model. So and with doing that, you can learn even more rare effects, of course. And you can do this higher dimensional as well. So you can go 3-dimensional, 4-dimensional. Depends on the data you have, right? If you have enough data, you can go pretty complicated here, get a very complicated model. but this then also means that you are collecting variance in a sense, of course. If you want, you can see this as kind of the depth in a decision tree, right? So if you go, for example, in a decision tree 5 levels down, right, this would be something like on a high level, similar to having an interaction term of 5 here, right? That means usually you come quite far with 2 or 3 dimensional effects. And if you want, you can also enable partly a hierarchical structure if you learn here interaction effects, for example, with product groups or with locations, so like a promotion for a given location or a holiday effect for a given location or something like that, or a product group if you want. And the second thing is once you have learned these factors, afterwards you can do something like a smoothing over it. So that means here this would be kind of the factors that you would have learned for different bins. So let's say after the first iteration, and then you can just smooth a functions like an orthogonal polynomial or something through it, and then take the values that come out of the smoothing as kind of the values that you use for the next iteration. This makes sense because this reduces just the variance, because most of the stuff is fluctuations. So if you know that they should make some sense in the different bins, right, they should be connected, you can do something like that. And if you want, you can also include prior knowledge via that. If you know that a feature is monotonic, or if you want something to describe over the time of the year, so like a seasonality or something like that, you can easily include it by describing these smoothing terms if you want. Okay. And then the plots that I've showed you, these are kind of the analysis plots of this method, if you want. So they come out of the training itself. So basically, because these factors are what is calculated, and this visualization then comes for free. So they can actually help a lot in the model development if you want. So it really helps if you want to find out how different features are correlated to the target and so on. And they're actually automatically generated. And here's what I said before. So you would see that the red line here would be the smoothed factors, so like the factors that the model has learned. And they might be different to the actual truths or predictions in the end. The reason is that you have correlations to other features as well, right? So then you don't see them in the marginal view, but of course they are reflected in the predictions itself. So it's kind of difficult to understand in the beginning why there is this difference. And actually deviations of the model, so real biases, you would see that the predictions are not directly with the target if you look in the learning after the last iteration. Okay, so then real brief, the characteristic I already said from the topology, it's similar to a generalized additive model. The optimization itself is coordinate descent, no gradient descent. You have something like a prerequisite that you bin the feature, which is not typical in most of the cases, and there are lots of regularization methods that I have not shown you. So for example, we're using conjugate priors for the features and so on to do another regularization on top of the smoothing. And if you want, there are similarities, as I said, from the model. We already said it. So then if you want coordinate descent is similar to backfitting in generalized additive models, but also to forward stage-wise modeling in boosting. The binning is kind of similar to what is done in LightGBM. So there they also do something like binning for very similar reasons, also for speed up. So that means it's kind of a mix of different methods, right? I already said it's in a sense off-the-shelf method because it's a pretty simple algorithm, as you have seen. It is robust and super fast because it's that simple, right? You have really few hyperparameters to tune. You don't have to do much data pre-processing like for neural networks or so. You can basically throw anything in. It's easily configurable for different data types like continuous ones, categorical ones, as I've shown you. Missing values are supported. I have not talked a lot about that, but it's just one other bin, right? Just a different category. You get these analysis plots that help you. You can easily make it more complex if you want by including many interaction terms. So far, you have to give them by hand. So we plan in the future that we do something like a mode where we would help you, like these are the most important interaction terms, right? So far, you have to basically provide them from the outside. And as I said, you can do multiplicative additive regression. You can also do classification. And also the other modes that I have to skip now, you get the slides, right? So like for the width prediction where you get out a full probability distribution rather than the pure conditional mean. So this is important for a case like automated replenishment. As I said, I dropped that, and also the elasticity prediction will drop. So this is something like yet another mode. If you think about generalized additive models, there are these things about scale and shape as well. So this is yet another application that we had, for example, for dynamic pricing. Okay, by that, I'm done. Maybe in the end, if you want, you can try it. So we have actually set up a hackathon where it would be great if a few of you would actually play around with it. This is actually for this case that I mentioned, like retail demand forecasting. So try to beat it. I have implemented a simpler and a pretty advanced cyclic boosting model. Would be cool if somebody can beat it either with cyclic boosting or anything else, right? It's super hard to beat it on that use case, I think, even with a transformer. But it would be great if somebody does. Okay, thank you.
Thank you for your great presentation. We have some questions on Slido. If you have any more questions, you can just write it down for room B09. And the first question is, what effect does the binning have and an independent variable is numeric? When the value is on the edge of a bin, a small increase can have a big effect.
Yeah, that's true. So if you have a continuous feature, at some point you have to decide about the bin widths, of course, right? So, and it can be that if you go from one bin to the next, then there's kind of a gap between the factors learned. But usually you do the smoothing afterwards that I've shown you, right? And if you do something like an orthogonal polynomial or whatever, a piecewise linear thing or so you would usually not see a big difference because these are the factors that are actually used later on. So usually you see a rather smooth thing from one bin to the next. If you would not do smoothing, it's correct. Then it can have a large effect in worst case.
Next question is, since it loops over the features, does the order of the feature matter?
It's a good question. Yes, the order of the features matter. If you don't want the order of the features to matter, you can easily just include a learn rate. So then it would not matter anymore. So if you basically do only small steps, so like a shrinkage method, so then it would not really matter. But if sometimes you want the order to matter, right? If you know what you are doing, you can actually use the order to actually include something like a hierarchy or even a sense of causality, right? So that means the order can be helpful. If you don't want it, you just use learn rate.
Next question is, does it scale well with lots of feature and or bin size?
For the bins, it's really no problem, as I said, so you can go as large as you want. It just learns an additional parameter. Of course, if you go to many bins, it means that you go low bias, and this also means that in worst case you can overfit, especially for categorical features where you don't do this smoothing, so I only do kind of the Bayesian updates. For features, in principle, it doesn't matter really because you treat them sequentially, right? The runtime, of course, gets longer because it's sequentially, but it scales. It just takes longer to train. But the training is super fast because the method is so simple with the sums.
The next question is, how computationally expensive is the deployment of this model?
It's actually, I would say, super cheap compared to most of the other methods. Again, because the algorithm is pretty simple and you can treat the features sequentially. I would say in principle, there are not many low bias methods like this that are cheaper, at least none that I would really know of. So from that sense, I think it's computationally really very cheap. What we don't have currently, but what would be easily to be developed, maybe something else for the future, is a completely parallelized mode. So at the moment, we run this on one node, so to say, but you could easily parallelize with things like Dask or whatever, right? So it is possible, but at the moment, this is not the case.
Last question is, if you have to name a couple of drawbacks of this method, what will it be?
Yeah, I think the biggest drawback, of course, if you compare it to deep learning methods, is that there is no sense of depth, right? So that means to learn something like what a CNN is doing, right? So that you learn typical hierarchical effects of the representation or something like that. This you cannot do with a shallow method. But this is not only true for this one, but for any method. But this would be compared to deep nets, compared to things like gradient boosting and so on. I think the biggest drawback would be that at least currently you have to define yourself what are the interaction terms, right? This comes for free in a tree-based approach. This can be an advantage and a disadvantage, but if you want to be hands-off, right, this is kind of a disadvantage because you don't get this right away. But maybe one could build something like that. Would be great if somebody does.
Again, thank you for the great presentation and for answering all these questions.
Thank you.